In 1895, Wilhelm Röntgen was experimenting with cathode rays, which are streams of electrons in a vacuum tube. While setting up one of his experiments in the dark, he noticed a glow on a screen he prepared for a later measurement. Turns out that his experiment was generating X-rays that made the screen glow. A few weeks after his discovery of X-rays, he was using them to take images like this one of his wife's hand. His discovery won him a Nobel Prize in 1901. Hi, I'm Mihai Kuciuk, and in this video we will look at some of the different types of ionizing radiation. I'll focus on alpha, beta, and gamma rays, as these are readily available from radioactive sources we have access to. I'm now in one of the labs at the Extreme Light Infrastructure Nuclear Physics facility in Romania, and there's a link in the description where you can check some of the cool stuff we do here. Later, we'll use these sources for some measurements, but first let's talk about what exactly these rays are and what makes each of them special. To take things alphabetically, alpha radiation is a helium nucleus consisting of 2 protons and 2 neutrons. What makes it ionizing radiation is that it moves fast, on the order of 50 million kilometers per hour, and it can rip electrons off along its path. Now, even at 50 million kilometers per hour, this is quite slow at the nuclear level, and we'll see shortly just how fast other radiation moves. Because it's slow, it spends a lot of time around those electrons that it rips off, and they pull back on the alpha, slowing it down even further. That's why alpha radiation is very easy to stop, even with modest shielding, and we'll see that happening very soon. But first, let's look at a faster particle. Beta radiation is nothing more than fast electrons, very much like the cathode rays that Röntgen was experimenting with. These electrons are about 10 times faster than alphas, on the order of 500 million kilometers per hour. They're lighter and harder to stop, and you can think of them moving through matter like a cyclist filtering through traffic. Gammas and X-rays are physically identical, so we'll consider them together. They are photons, just like visible light is, but with much higher energy. Being photons, they travel at the speed of light, about 1 billion kilometers per hour, and usually pass through matter in a straight line undisturbed. But every so often, a photon hits something, causing ionization, and may scatter away or disappear altogether. This makes them much harder to stop because we rely on this probability that they interact rather than being certain they do, as is the case for alphas and betas. These photons are more likely to interact with dense materials. Let's look at this X-ray of my teeth, for example. Here we can see a filling that's much denser than the bone around it, thus casting a darker shadow on the image.
Let's put all of this into practice and see if things check out. We'll use this detector that has a very thin entrance window such that it can detect every type of particle. We'll use alpha, beta and gamma sources, and we'll try shielding the radiation from each with different material, a piece of paper, some aluminium and some lead. But first we need to keep in mind the background measurement when there's no source at all present. Earlier it was 10, now it's around 12 counts per second due to statistical fluctuations. We'll fill this table in with our measurements after subtracting the 10 counts per second background to have a picture of what's going on. Let's start with an alpha source. Our count rate rises to 160 counts per second, so we'll write down 150 in our table after subtracting background. We now add a piece of paper in front of the source. And the count rate dropped back to essentially background, so we stopped all of the radiation. Now aluminium. And we get the same result. Now we're placing some lead in front of the source. With lead we also get background within statistical fluctuations. We are now switching to the beta source. Let's now move to the gamma source. This is sodium-22, so these are fairly high energy gamma rays at around 1.3 mega electron volts and 511 kilo electron volts. While this source also emits positrons, they are stopped by the plastic case that contains the source, so we only get the gamma contribution. Let's now look at our data and normalize everything to percent. That tells us what ratio of the radiation we still measure with shielding compared to no shielding. This gives us the table with our final results of how much each type of radiation is left with the different types of shielding. For alpha radiation, things are super clear. Even paper stops all of the particles. Let's consider the gammas now. They don't care at all about the paper and aren't that much impressed by the aluminium, but almost half of them get stopped by the lead. Think back to the X-ray of my teeth. A denser material made a darker shadow, and this is exactly what we see here too, with lead stopping more gammas than the lighter aluminium. Now betas are funny particles and require more context. Beta decay, the nuclear process that creates these electrons, produces them with a very wide range of energies. The very low energy electrons do get stopped by the paper, but most of them get through. What about the aluminium and the lead? Our measurements give very low numbers, but we can't just ignore them. What happens is that when you stop high-energy electrons, you generate Bremsstrahlung radiation. Those are photons just like X and gamma rays, so they obey the same laws we saw before. They get attenuated more in the lead than in the aluminium. So we can conclude that the betas themselves get stopped by the aluminium and the lead, even if these aren't the perfect kinds of shield against betas.
Can you think of uses for the different types of radiation based on their range? How about protection against them? Let me know in the comments below. Special thanks to the Extreme Light Infrastructure Nuclear Physics Facility for letting us film in the lab, and thank you for watching.